So what we're going to do is talk about problem set 6. Just for reference, or to remind people, we're omitting number 3 and number 11. So for this, because we gotta make some cuts, and I think I'm gonna cut a few of these in here when I get to it. All right, and then for number 7, this was the second page of problem set 5. These two I did in Thursday's lecture. That video will be posted shortly on YouTube. These four, some were done in class. If we want to go over one of these, I'm fine with that. This one, probably something like it with hanging won't be on the test, but stuff like these 3 will. Now for problem set 6, number 1, you have a hill that is 30 meters high, so H is given, and then we have a mass. It's loaded into a spring cannon, so there's a cannon, and the cannon is fixed. The spring constant is given, and the compression distance is given. There is no friction. Yay, no friction. So what we do with this is we're going to do it with letters, and then you guys can come through and pick apart the numbers. So what was the stored energy in the spring before it was released? So the potential energy of the spring is 1/2 kx squared. The answer that you get will be in joules. Remember that x, I gave it to you in centimeters. Convert that to meters. And so that would be part 1. Part 2, what is the gravitational potential energy of the mass with respect to the bottom of the hill? Well, potential energy gravity is just mgh. So you just multiply that together. And again, potential energy is measured in joules. Now, what is the kinetic energy of the mass when it is at the bottom of the hill? So at the bottom of the hill, what do we know? That the spring has uncompressed or decompressed, and that's at the bottom of the hill. So this kinetic energy is equal to the potential energy of the spring plus the potential energy of gravity. So what you do is you take those two quantities and add them together. And that will give you the kinetic energy of the mass when it's at the bottom. Because there's no friction, no energy is released into the greater system of the universe. So the mechanical energy is conserved. What is the velocity of the mass when it's at the bottom of the hill? Well, that kinetic energy, there is no potential energy, 100% has been converted, so it equals 1/2 mv squared. So 2ke over m is equal to v squared, or the square root of 2ke over m is equal to v. And that's the velocity of the mass. Part 5, the last bit, what's the ratio of the energy before over energy after? Since energy is conserved, the energy before is equal to the energy after. So energy before divided by energy after is equal to 1. And so that's problem 1. Now I leave it to you to plug and chug. That's your bit. For number 2, I'm making sure I'm on the page. Excuse me. For number 2, we have a mass that's given, and it is loaded into a spring cannon. The K is given, and then we have the compression distance X is given as well. All of this, once the spring is released, it crosses a surface where the coefficient of kinetic friction is 0.6. And just so we have visual record. So those are the problems that we're doing. Before the mass is released, what is the potential energy of the spring? Well, once again, potential energy of the spring is 1/2 kx squared. What is the kinetic energy of the mass the moment after the release? So if we consider that as point A and that as point B, then the energy at A is equal to the energy at B. At B, it's fully released, it's entirely kinetic, so the kinetic energy at point B is the same as the potential energy of the spring. So take that number, write it again. But understand why. What is the initial velocity of the mass? Well, this kinetic energy is equal to 1/2 mv squared. So 2 kinetic energy over m is equal to v, and you get the same thing over here. V is equal to square root 2ke over m. Now, how far does it move before it comes to a stop? I'll say that distance is d. When it comes to a stop, there's no change in potential energy, so you can just forget about it. Potential energy is in gravitational. But all the energy at point C has been spent. There is no kinetic energy, there's no potential energy, there's nothing. So what we have here is that the energy at B minus the energy released through friction, the work, is equal to 0. Or EB is equal to the work. You've got this number from here. Let's look at work and play with it for a bit. It's a mass. It has a normal force. It has a mass and gravity. It has a friction force. And we know these relationships. The sum of the forces vertically is 0, which is equal to Fn minus mg. Friction force is mu sub k times normal force. You move that over there, and normal force is mg. So this becomes mu sub k mg. The work, force times distance, so this is mu sub k mg d, where d is the distance. So EB is equal to mu sub k mg d. So EB divided by mu sub k mg is equal to d. And so those are the answers that I'm looking for. So in the first example, we had a pure conversion from potential to kinetic with no friction. Here we have a potential to kinetic to nothing because of friction. And that's number 2. Now, as I've said before, problem 3 and 11, I've decided to eliminate because we just don't have the time. Number 10, let's skip to that for just a moment. Number 10 is a study of an inelastic collision. They stick together. Really, this is just a play in understanding a collision. It's an inelastic collision, so the initial momentum is equal to the final momentum. The initial momentum is m1 v1 plus m2 v2 is equal to m1 plus m2 v final. So v final is m1 v1 plus m2 v2 over m1 plus m2. In certain circumstances, well, really in all the circumstances, these values have been given. The one thing that you need to pay attention, so really all it is for the first one is you just plug in the values and boom, there you go. But for number 3, it has that negative velocity. And the one thing that you need to know is V can be positive or negative. So if I say V is equal to negative 20 meters per second, plug in negative 20. If V is 20 meters per second to the right, then you know I'm playing with magnitudes. And the V that you plug in is equal to positive 20. If I say V is equal to 20 meters per second to the left, you know that the velocity is going to the left, and so the number that you plug in is negative 20. So velocity can be negative. In fact, the answer that you get can be negative, particularly in the third one. If you get an answer of negative 20, you could say the velocity is 20 meters per second, or you could say 20 meters per second to the left. Either one is fine. But number 10 is just a simple plug and chug. All right, number 4 through 9. What I want you to do with these guys earlier in the semester in problem set 3, we used the equations of motion to determine the final velocity at the bottom of the hill. Today what we're going to do is we're going to determine that same velocity through a different method. In this particular case, we're going to use energy. Now, as I'm looking at this, I'm going to make another decision. Don't do 7 or 9. Focus on 8. Number 8 was done Thursday in lecture. That video will go up shortly this afternoon. Really, when I'm trying to trim the fat off of here.
So altogether 3, 11, 7, and 9.
I need 4 through 6 and 8.
4 through 6 and 8.
Yeah. And once again, in the lecture on Thursday, I broke this down according to all the different variables and possibilities and worked through it. In this specific case, I've given you numbers. The velocity that you get for problem 8 should be the same as the velocity that you got for problem set 3, number 8. They should match. So let's just focus on 4 through 6. What I'm going to do is I'm going to do it generically. Really, number 5 and number 6 are kind of the most general. This one has no friction, which is awesome. I'll talk about how to deal with that later. But for this, you have yeah, we're going to do number 5. Really what we're going to do is we're going to do number 5 and 6 at the same time. And then 4 will just knock out really quick. The inclined plane has an angle of elevation of theta. The mass is at the top of the hill, and it has an initial velocity that is given. You have a distance down the hill that's given. You are given a coefficient of friction. I even give you a mass. The question is, what's the velocity at the bottom of the hill? Now, because there is friction, and in the general case, assume friction, the initial energy minus the energy removed through friction is equal to the energy final. Now, initially, this thing is moving. So the initial energy has a kinetic energy and a potential energy. At the bottom, it only has kinetic energy. It's at the bottom of the hill, it has no potential, so it's entirely kinetic. The kinetic energy at the beginning is 1/2 mv0 squared. The kinetic energy at final is 1/2 mv final squared. Now we've got to figure this stuff out in the middle. The potential energy is not measured by that length, it's measured by that height. So the potential energy is mgh. This specific height is not given, but you. Yeah, you're going to use trig. Sine of theta is h over L, so h is L sine theta. This means that the potential energy is mg L sine theta. Now for dealing with work. This thing is on an inclined plane. That's the normal force. That's the velocity, that's the friction force. So you have to draw out a quick force diagram. You go through the steps that I've gone over so many times. You know that it's not penetrating the surface. Yes. Or no, the number 5, this is number 5 and number 6. at the same time. Number 5 and 6 are just different sets of numbers. This is Fn minus mg cos theta. So the normal force is mg cos theta. The friction force is mu sub k times normal force. So this is mu sub k mg cos theta. And the work is force times distance, which in this case is the length L, because that's the distance, will give you mu sub k mg L cos theta. So that goes in here. Minus mu sub k mg L cos theta. One of the things that you see is there is an m in every single term. So the mass truly isn't necessary. The other thing, so what I'm going to do, I'll do this step by step. 1/2 V naught squared plus Lg sine theta minus mu sub k GL cos theta equals 1/2 VF squared. Now I'm looking to solve for final velocity. Multiply both sides by 2. V naught squared plus 2Lg sine theta minus mu sub k GL cos theta is equal to VF squared. And then VF is equal to the square root of V naught squared plus 2Lg sine theta minus mu sub k GL cosine theta. And that's what we have. For each of these systems, the masses don't matter. Mu sub k is given, g you use 10. Theta is given, V naught is given, V naught is 3. L is given in each of these cases. So for number 5 and 6, that's the equation that you use. Now this is the advantage of doing it this way, is rather than sitting and plugging and chugging a full set of numbers, you get the general equation, plug in the numbers once, now you got 5. Plug the new set of numbers in, now you got 6. What makes 4 so not exactly different, but is simplified, in number 4, mu sub k is equal to 0. So V final simplifies to V naught squared plus 2Lg sine theta. And you just have to figure out that part. So really, in the course of 2 pages, or 2 small pages, you can do all 3 problems. Because solving it generically is better. Once you've got it generally, the specifics of the situation do not matter.
So for problem 4, you don't even have to go back through and work it out.
I would go for
plug in 0 from mu sub k.
yeah. I mean, it's really, you could treat this as the solution for 4, 5, and 6, but mu sub k is 0.
But then whenever if you were to go back and do it, you just would take out the work component.
Yeah, I would. Yeah, if there was no friction, that would go away, which means that goes away, that, and that all disappeared. And this becomes completely unnecessary. Yeah, if I gave you 4 on a test, I would just do this, that, and this. Like it would come out pretty quickly. All right, and that is problem set 6. But really, what I need you guys to do is just understand the technique of how to go through this, how to take out the energy through friction, how to calculate the initial and final positions. All right. And now that I remember, I don't have to steal.
So problem 7 on problem set 7 is what we did yesterday, except all 4 children go to the...
Yes. Yeah, that actually simplifies things incredibly by doing that.
And then 8 is like, we did that one verbatim now.
Yeah, we did 8 pretty much verbatim, but different numbers. 7, in Thursday's lecture, one of the 4 stayed at the edge. But you could make the necessary adjustment. The 3 becomes a 4. That middle term goes away. So for, just here to make things easier, because we got the test next week. Eliminate number 12. Really, it's just going to be 9, 10, and 11, or a variant of it. So what we can do is just roll through these. In 9, 10, and 11, a valid question to ask, sort of like on the test for 9, 10, or 11, is this thing moving or will ever move? And my answer for this is no. It is at rest. It is not moving. It will never move. So in 9, 10, and 11, you can say the following: that the sum of the torques is equal to 0, and that the sum of the forces vertically is equal to 0. Sum of the forces in X is equal to 0, but that's not relevant. To do this, what you typically have to do is focus on, well, this one's obvious. F. You sum the torques around a rotation point. It doesn't matter which rotation point, but you need to wisely pick one that will eliminate an unknown. So what I'm doing is I'm marking my rotation points for summing the torques. By picking a point of rotation exactly where one of the forces exists, you can eliminate that unknown, because torque is the product of two things: the force times the distance from that force to the rotation point. By picking this, the distance from the force to the point is 0, and F times 0 is 0. So in the case of number 9, the sum of the torques is M1G R1. M1G is the force, R1 is the distance. The next torque, M2G R2. M2RG or M2G is the force, R2 is the distance. F2 is the third torque. Its distance is R2 plus R3. And then the last force, M3G, R2 plus R3 plus R4. So you have to figure out what the torques are with respect to this particular rotation point. Now comes the right-hand rule. The rotation point is there. R1 is to the left. M1G is down. Torque 2 is to the right and down. F2 is to the right and up. And M3G is to the right and down. And what we're doing is we're figuring our signs. To the left of the rotation, down, thumb up, positive. Force is to the right of the rotation point. It's down, into the page, negative. That force is to the right, but it's up, out of the page, positive. This is like this, to the right and down, right, down, in, or negative. So the right-hand rule is used to determine the signs. The only unknown in this equation is F2. So M2GR2 plus M3G R2 plus R3 plus R4 minus M1GR R1 is equal to F2 R2 plus R3. And so that's F2. So it's just algebraic manipulation now. Now that F2 is a known quantity, you could just redo the calculus, but the easiest way is to sum the vertical forces. Forces up equal forces down. Sum of the forces vertically is 0. F1 plus F2 minus M1G minus M2G minus M3G so M1G plus M2G plus M3G minus F2 is equal to F1. And that's number 9. So you just plug and chug to get F1 and F2. And really, it's just 10 and 11 are just lather, rinse, repeat. All you have to do is correctly construct these equations, and then everything else just falls into place. Identify what you know and what you don't know. Pick a rotation point at one of the unknown points. And then you could do 10 and 11 on your own. It's not that big of a stretch. So, I mean, do you want to do 10 and 11? Or, I mean, it's... Once you know the system and once you can apply the right-hand rule, then everything is about just algebra after that. So, and I think there is, take a look at, there are a few other examples, like when I did the torque bar in class, that those show some good examples. So that's problem set 6 and 7. It's not that bad, especially after we trim it down. All right. So what I've figured out is we've got today, we've got Tuesday in class, and then on Wednesday I do have a review session scheduled. It's a bad time because it's during the day, but that's all I could get. And yes, the video will be recorded and posted and all that stuff, so it will be available. So we've got some time to review. Now, if you want, I can kind of go through one of the tests, or we can wait until Tuesday, whatever you guys are. Probably what I want to do is I want to have a larger class, because there's only 4 people in the room, and well, actually 5 including me. So what I'm going to do is over the weekend I'll take a look at the multiple choice and put up the answers, and then on Tuesday we'll go through one of the tests. The one that I'm looking at is October 20th of last year, and I mean, when you look at this, you go, yeah, a rotation, an Atwood's machine, a torque bar, and for the appetizer was right hand rule. So it's exactly what it was that I've been saying. So what we'll do now is we'll just end it, and then we'll get back on Tuesday.
Yeah, maybe like 10 minutes there. I got like half of number 10 from.
Okay, let me turn this off.
Yeah.